All right. So is there any question from the last class? We were doing this problem, I remember. This was the problem that we were solving. Is there any question from whatever we did up until this point? Or any other question regarding to the topics that we have covered, if you might have gone through those
Your
topics?
voice is cutting out.
Oh, there is, okay. I changed my ISP. That was the reason for yesterday's meeting to be, that was basically postponed. Is it still cutting? Just give me 1 second. Okay, is it clear now? Is it or is everyone facing this problem? Okay, I think you had, okay, you're back again. Can you hear me, Taha? Taha, can you hear me? Am I, is it? Okay, anyways, so I'll assume for now that there is no question from the last class. If you have any question, you can always stop me and we can, I'll get to your question, right? You can post it in chat as well, or you can unmute yourself and ask the question. So basically, this is what we were doing. We were doing the addition of vectors. We were seeing how we can add vectors together. So I'll just quickly recall or go through what we did. We did this example where we had a point P, and there was some 4 newtons of force acting on that point P in the upwards direction, and 20 newtons of force which was acting in this direction. And we basically we added these two forces vectors to see what would be the resultant effect on this point P. And we saw that it was 20.4 newtons, which meant that with this amount of force, this point P would be pulled in this direction. So to compute the direction, we made use of this expression tangent theta, which was, I showed you over here, how do we get to this expression? You don't have to derive it or anything, just you can remember this formula. And if you want to understand where it comes from, then that's what we did in the last class as well. Just use this formula, and in this, the angle theta is given by the tangent inverse of the y-th component of the force divided by the x component of the force, right? So in our problem, what were these components basically? Remember, let me go back. So the y component was 4 newtons, and the x component is this one, which is 20 newtons. So this is, again, our coordinate system is defined as y-axis is upwards and horizontal axis is x. And so 4 newtons, Fy is 4 newtons, Fx is 20 newtons. And so you'll just take these values and you will put them here. So we get theta is tangent inverse of, wow, my memory is lacking. What was it? Fy was 4 and Fx was 20, right? So 4 over 20 newtons, and the newtons, we have 4, we have 5. And so tangent inverse of 1 by 5 is 11.3 in degrees, right? So that's the angle. This is the angle that this resultant vector would be making with this x-axis, right? So that's 11.3 degrees. So this means, in turn, the whole thing basically meant is that if I apply 4 newtons of force in the upwards direction on this point P, let's just call it a ball or a book, and you apply 20 newtons of force to the right direction in the horizontal direction, the resultant of these two forces would give you this force R, which is 20.4 newtons, and at an angle 11.3 degrees to the horizontal direction. So that's how, if this point P, you can imagine it as a book, that's how it would move with that much force, right? So that's what we did in the last class. Is there any question whatsoever? Any question?
No, sir.
Okay, perfect. So now there is another way to approach the similar problem. You might not be using this method as often, but it's there in your course, and so we'll just go through it. It's a graphical method of solving the same problem, and to apply this technique, you have to take some steps. What I'll do is I'll just get rid of all of this, what we have over here. Let me, and we'll start from the beginning. All right, so that's that. Right, so basically you have the same problem. The statement of the problem, everything is same. Now, so the problem was simply in y direction, we have 4 newtons of force applied on this point P, and in the horizontal direction, we have 20 newtons of force applied on this point P. What would be the resultant force, and what would be the angle this resultant force makes with the horizontal axis? So what we can do is, we'll first of all, the first step in this case is, because we will be using you can say you'll be using a ruler or a graphical approach for this problem. So you'll be using a centimeter scale because you don't really need a meter scale when you're working on a paper, right? You just use a centimeter scale. And so because you will be writing your forces in terms of how many centimeters I can draw on this paper. So you need to define the scale. That's the first step. You'd be defining a scale for your problem. So in this case, what you would be doing is, you can take, for example, what I'll take is 1 centimeter is equal to 2 newtons. Now, why this particular scale? Why not any other? Well, this one makes sense, because if I said this is not really an equal to sign, you put 3 lines like this, which means equivalent to, or you can say that you're representing 2 newtons of force by drawing a line of 1 centimeter. That's what this means. So this scale is an appropriate scale for this problem. Why? Because you see, you have a force in y direction of 4 newtons, and in horizontal x direction, it's 20 newtons. So now, if you were to take a scale, for example, let's say you took 1 centimeter as 1 newtons, then you would have to draw a line that is 20 centimeters long in the horizontal direction, right? So it starts from 0 centimeter, and it should be at exactly 20 centimeters long. Now, that is not really convenient when you're drawing on a paper. So if I can take a scale that is 1 centimeter is 2 newtons, that just means that if I draw a line of 1 centimeter, that corresponds to a vector of 2 newtons, right? So I need 20 newtons. So I'll draw again 1 more centimeter, that makes it 2. So how many centimeters would I have to draw to represent a force of 20 newtons? Any idea? It would, sorry?
Will be 10 lines, I
Yeah,
guess.
exactly. It would be 10 centimeters, right? So every centimeter corresponds to a force of 2 newtons. So that means 10 centimeters would correspond to a force of 20 newtons. So that's how you'll draw your horizontal force vector. Now, in the exact similar fashion, you'll draw a vertical force vector, which is 4 newtons, right? So how many centimeters that would make? That would make 1 and 2 centimeters, right? So well, of course, this is not an accurate drawing, but when you're doing it on a paper, you'll be using a centimeter scale, and you'll be drawing it accurately. So that would be 2 centimeters, right? Which would correspond to 4 newtons of force. The next step is very simple. You will just draw a dotted line, in a horizontal dotted line from the head of this vector, which is vertical, and you draw a vertical line from the head of the horizontal vector, and you join these 2 points. The intersection where these 2 lines meet, these dotted line means, you will draw a line in diagonal from that point of intersection of those 2 dotted lines in this way. So it should touch this origin. We'll call this point origin. Now it's very simple. All you have to do to find this resultant, now this was the resultant vector, right? This is the resultant vector as we discussed in the last class as well. To know what would be the force corresponding to this R, you'll just measure, you'll put a scale on this, and you will measure it from this point, its tail to its head, and you'd get an answer in centimeters. Now that answer in centimeters, you will simply convert it to newtons using this conversion. 1 centimeter meaning 2 Newton. And so you would have the resultant, and this would again be equal to what we computed in this trigonometric approach, which was 20.4 newtons. So you would get the same result, and you should expect the same result, right? Because the problem is same. It's just another approach to the problem, right? So you'd get, look at me, I forgot again, what was it? 20.4 newtons, yeah. 20.4 newtons. And now the question is, how do I measure this angle? Well, that's very simple. You'll use a protractor, and you will put it, and I'm sure that you know how to use a protractor. You'll put it like this, and it's shaped like a D, and you'll just put it, and you'll start measuring from here, and you'll measure this angle, and let's call it theta. Whatever value you get, you should be getting 11.3 degrees. So that's how you approach the same problem in a graphical approach. Now, again, like I said, you'll not be using this approach. Typically, you would not be using this approach. You would be following the trigonometric approach. But is there any question in this method? Is it clear, or is there any question?
No.
Perfect. Right. So we can move forward now, and we'll move to this part. Here we have some of the measurement ranges, right? So, and the corresponding instruments that we can use to measure these ranges of lengths, with what accuracy we can do that. So for example, you have a material or an object whose length is greater than 100 centimeters. Anything whose length is greater than 100 centimeters, it's always feasible to use a measuring tape to take the measurements. You are aware of what a measuring tape is, right?
Yes. Yes.
Okay, perfect. So the accuracy for your measuring tape, it is accurate to 0.1 centimeters, plus or minus, right? So this is the
What does that
uncertain.
exactly mean? What does the accuracy exactly mean?
The accuracy, it really, what it means is that you know, your measuring tape is here it starts from 0, and then you have these small lines, 1, 2, 3, 4, and then you have a bit of line like this, which is like this, and then you have 5, 6, 7, 8, 9, and then you have something like this. So you have, this is your 1, right? Suppose this is your 1 centimeter. So the accuracy means that the least value that I can measure for this, which is 0.1 centimeters, right? And then you have 0.2, then you have 0.3, 0.4, and then this is 0.5. So is that clear?
Yes, sir.
Right. So here are some of the examples. You can just look at them. It's a waistline of a person. You measure your waistline using a measuring tape. It's an example from everyday life as well. Then we have a meter rule. Now, any range of length that lies from 5 centimeters to 100 centimeters, you can use a meter rule. And the accuracy of a meter rule as well is 0.1 centimeters. They're more or less, they're the same thing. This one is a bit more flexible, while a meter rule is a fixed instrument. And we can use a meter rule to measure height of an object, or well, basically you can use it to measure the height of any object. Then we have Vernier calipers. Now we'll talk a bit about detail about them, as you can see over here. But a Vernier caliper is used to measure lengths from 1 centimeter to 10 centimeters. And they are accurate to about 0.01 centimeters, and you can use them to measure diameter of a breaker. Are you aware of what's a breaker? It's a circuit breaker, and it's something like this, and there is a switch on it which can flip up and down, basically. So it's kind of small in size, and you can use Vernier calipers to measure the thickness of such object. You can also use Vernier calipers to measure the depth of anything, of any object. You can use it to, and I will talk about that when we start discussing Vernier calipers. Then you also have the next one is micrometer screw gauge. And a micrometer screw gauge is used for lengths which are even smaller than 2 centimeters. So the name suggests it is used to measure lengths which lie in the micrometer ranges, and its accuracy is 0.001 centimeters, which is a micrometer, basically. Millimeters, sorry. Now, thickness, you can use a micrometer screw gauge to measure thickness of wires. So if you have used or seen any circuits or anything, you know, a wire is pretty tiny, and you can put it in between the anvil and the spindle of, now we'll get into what these things are, right? So it's like this, and I can place a wire like this between this, and you can measure. We'll see that when we discuss these instruments in detail. So let's start with Vernier caliper. Now, here you see, you can see a Vernier caliper. Are you familiar with these instruments, Vernier calipers and micrometer screw gauge?
I'm familiar with the micrometer screw gauge, but I don't really understand the whole concept of Vernier calipers. It's a bit confusing.
Right. Okay. So So basically, this is what a Vernier caliper looks like, and again, it's just an instrument which is used for measuring. And this Vernier caliper, it consists of a main scale, which is this scale that you can see over here, this one, and it's fixed. So it's just like a scale that you would be normally using. On top of that, you have a scale which moves, and it's slidable. So it moves in one dimension. It can move left or right, right? And now you can use this instrument to measure the diameters, internal and external, both diameters. You can see that this part of this instrument is used to measure external sorry, I mean internal diameters, and this one is used to measure external diameters. So for example, consider you have a glass, and you know a glass is something like this. There is some thickness to it. It's a mug or whatever, right? What I can do is I can place this mug upside down on this. I thought that I could rotate this, but apparently I cannot. So we'll just try to draw it upside down. So it will be placed something like this. And you can then use the scale which is movable. Now this thing is attached to this movable scale, and you can open the scale to a point where these jaws or tips are touching the diameter or the circumference of this cup, right? So the edges of the cup are being touched, and then we can use those to measure the internal diameter. And I'll tell you how do we read this Vernier caliper as well. But in the similar way, you can, for example, you have a ball, you can put it in between these jaws. So this one is a fixed jaw, and here you have a jaw which is movable, and it is attached to this movable scale. So then you can just place it in between, open this movable jaw enough so that you can put this in, and then close it back, and then you can read the scales to find the diameter of this ball as well. So any question up till this part?
No, not at the moment.
Okay, so for example, if you were to record the diameter of this ball, you would basically put this ball inside this, and you would close the jaws. Then you would read the main scale. That's the first step, right? So this is your Vernier scale, and this is the 0 on your Vernier scale. You would record what is exactly to the left of this 0. It's kind of getting difficult to explain everything on this diagram. I think we have a clear picture. There's an example over here. So I'll use this example to explain what I mean. So let's read the example very quickly. We have a reading on Vernier caliper. When the object is between its jaws, it's 2.55 centimeters. And here we have both main and Vernier scales, and the readings are shown without any object between its jaws. So what we have to do is we have the length, apparent length. This is the length which is measured on the Vernier caliper. And we need to figure out the actual length of the object. So how do we do that? We need, what do we see over here? We see that these zeros are not aligned with each other. So the first step is that the zeros of these two things must have been aligned. If they're not aligned, what do you call that, by the way? If these zeros are not aligned together, that's called a zero error, right? So there, when you were starting your measurement, your scale was not set to 0. So there has been some zero error in the scale. So you would have to get rid of that zero error. Now, if you look at this diagram, you see that there is a zero error of about, so if that's 5, that's 1. So it would be around about 0.22 or 0.02 centimeters. So we'll have to eliminate that zero error. And how do we do that? It's very simple. You can see that this 0 is to the left of this main scale, and so the zero error is negative 0.02 centimeters. So that's the zero error. If I eliminate the zero error from the reading that my Vernier scale or Vernier caliper took, then I can find out the actual length of the object. So that would be, we're given 2.55 centimeters, and I have to eliminate from this the zero error, which means minus. So eliminate means just get rid of it. So we'll subtract from it. And the zero error is minus 0.02 centimeters. And this gives you 2.57 centimeters, because these two minus would make a plus, and then you'll be just adding 0.02 to this value. So that's the actual length of my object, 2.57 centimeters. So what we did is we placed an object in between the Vernier caliper, and we recorded the reading on the main scale, which was to the immediate left of this Vernier scale, which over here you can see is this reading, right? This one. And then what you do is you will read the Vernier scale, and the Vernier scale is read by counting these as 0.01 centimeter, 0.02, 0.03, 0.04. And then what you do is you add whatever value that you had from here to this 0.0 whatever you have from here. So there is no exact reading that I can read from this Vernier scale. I think if there is any more example in this, no, there was only this example. In the next class, what I'll do is I'll bring a problem which shows you how to read the Vernier scale, Vernier caliper, basically.
So this is the estimated zero, what is that called? Zero error reading, right? The one you derived? Like the 0.02,
the one that I
is
wrote
that the
for the zero error. Yeah,
that's not
it's an
the
estimate.
exact, right? That's
No,
not
no,
the
it's
exact
an
reading.
estimate, and the reason it's an estimate because we cannot really tell, right, how much of this is there. You are just estimating that it's approximately 0.02 centimeters, and it's a very good approximation as well, because you see that this is 1, right? So if this is 1, then something that is very at this point, it could be 0.02, it could be 0.03 as well, right? Because 0.05 would lie somewhere over here. If I'm not wrong, it would lie somewhere over here. So yeah, you're right, exactly. So this is an estimated reading for the zero error.
So what if I come up with 0.04? So my whole answer would be wrong, right?
You'd come up with 0.04?
0.04 or 0.03. So what if the answer is
Okay,
wrong?
so if you
So
were
that would
to
be
come up
2.56. Right?
So if it lies somewhere around 2.56, then you know it's closer to 2.57, right? So you'd choose 2.57. You should look at this. I think I should zoom in a bit. Yeah. So you see that this is 0. This is 0.012345. So you see, you have to. What I should do is I should even decrease the size of this pencil. So this is 0, 1, 2, 3, 4, 5. So that's 5, and that's, you can see that now this is somewhere which lies exactly halfway between these two lines. So then it's a good approximation. You could take 0.02 or 0.03, or you could also take 0.025, which lies in between the two. So is that clear?
Yes, that is clear.
Okay. Just zoom. Right. So basically what I was saying is I'll bring in the next class, what I'll do is I'll bring an image, which is a proper image where you have some object lying placed in between the Vernier caliper, and then I'll show you how do we take readings from the Vernier scale and the main scale, and how do we combine them together to form the final reading as well. But similarly, you also have this thing which is called a micrometer screw gauge, and it's also a measuring instrument, and it has a main scale, which is this one, and it has a thimble scale, which is this one. It is used, the micrometer screw gauge is used to measure objects which are very small. They're even smaller than the objects that we can put inside a Vernier caliper. So like I gave you an example, if you think of a wire, you could place a wire in between these two. It's you can measure very small what do you call that, diameters with a micrometer screw gauge. So you could place a wire in between, and you could close this this spindle, because the anvil is fixed. So when it touches the wire, and then you can read off the scale and the thimble. So I'll tell you exactly how do we do that. It's my mistake, actually. I should have brought a diagram where you have you really have something in there. But to read a micrometer screw gauge, what you do is you will turn on, you'll turn over this thimble, so it's rotatable, right? So you'll turn it until this spindle touches whatever whatever lies in between the anvil and the spindle. So the spindle would be touching the object, and then you would turn the this ratchet. It is also movable. You will turn it until you hear a noise, basically. So it will click, and so then the spindle and the object, they would be kind of locked together, right? So it would be you can say that there would be a grip that would be formed between the spindle and the wire, right? So then once that is done, you will pay your attention to this scale. It's also it's the main scale, and the readings on this main scale are in millimeters. Now you'd read the main scale, which is to the left of the thimble. So for example, this is the thimble, so anything that is exactly to the left of this thimble would be your reading. And once that reading is taken, you would note it down. So let's say whatever it is X. Then you would start reading the thimble. And the thimble would be read as from, so you can see here, you have 15, you have 20, whatever is in exact correspondence to this